The rapid development of machine learning techniques, computational capabilities, and data acquisition has entered a new era for sea ice extraction, a crucial problem in polar navigation, terrain analysis, and polar cartography. Deep learning-based approaches have gained significant attention in the last 5 years, converting the sea ice extraction problem into a semantic segmentation problem. This involves determining the category of each pixel via post-classification procedures after regressing the category probability using deep convolutional neural networks. A literature search was conducted to visualize the co-citation network of relevant publications, highlighting key themes and research areas associated with sea ice extraction, particularly in remote sensing and SAR. Remote sensing techniques, including visible, infrared, passive microwave, and active microwave remote sensing, are used for sea ice extraction. Visible, infrared remote sensing provides texture information but has limitations due to polar day and polar night phenomena and orbit inclination. Passive microwave remote sensing offers global coverage but has low spatial resolution. Active microwave remote sensing, specifically SAR, provides higher resolution capabilities, making it suitable for fine-scale sea ice mapping. Machine learning methods have made significant applications in sea ice extraction, with recent reviews summarizing the advantages and disadvantages of sea ice classification methods based on SAR data, the advancements of GNSS-R data in SAI, and the comprehensive analysis of sea ice sensing using polarimetric SAR data. This review aims to provide a comprehensive overview of sea ice extraction, including algorithms, datasets, applications, and future trends, focusing on deep learning-based approaches in the last 5 years. This review provides a comprehensive summary of the latest sea ice extent (SAI) methods developed in the past 5 years, categorizing and analyzing these methods, considering associated datasets and subsequent mapping applications. It also incorporates the latest advancements in technology to assess challenges and future developments in SAI through the utilization of large-scale models. Recent publications on SIE have primarily focused on classical image segmentation methods, which rely on statistical algorithms combining probabilistic models and classical classification methods with texture or polarization features to generate sea ice type maps. For instance, a new Bayesian risk function was proposed in 20 to minimize the likelihood ratio for polarimetric SAR data supervised classification. This method utilizes the Bayesian theorem to compute posterior probabilities of each class at each observed location based on texture features extracted from the gray-level CO occurrence matrix (GLCM) of the image. Another significant approach is the MAP-guided ice classification, MAGIC 23, which labels each pixel in the SAR imagery as ice or water, modeling the labeled pixels as a Bernoulli distribution to estimate ice concentration. These equations governing these methods, such as the Bayesian risk function and the computation of posterior probabilities, are crucial in understanding the underlying principles of SAI. The use of large-scale models and advanced algorithms is essential in improving the accuracy and efficiency of SAI methods. This review aims to provide a comprehensive overview of these methods, highlighting their strengths and limitations, and identifying areas for future development. The co-citation network for SAI research is visualized in Figure 1, where the frequency of keywords is represented by the size of nodes, and the strength of their relationships is indicated by the width of linking lines. The publication year is depicted through color variation of the nodes. The review is structured as follows. Section 2 provides detailed insights into recent methods for SAI. Section 3 summarizes currently available open-source datasets related to ICE. Section IV outlines downstream tasks and enumerates the generated geospatial information products resulting from ice extraction. Lastly, Section V highlights areas where future developments are needed. In the realm of sea ice classification methodologies, various approaches have been employed to differentiate between ice and water in synthetic aperture radar (SAR) images. The Bayesian classifier has been extended with the introduction of a Gaussian incidence angle (GIA) classifier, which replaces the constant mean vector with a linearly varying mean vector. This modification enables near real-time ice charting and has been utilized to generate classified winter time series of sea ice in the Mosaic campaign regions, providing reliable support for navigation. Maximum likelihood estimation has been used to compute the probabilities of ice and water in observed SAR images. Unsupervised mixture Gaussian segmentation algorithms have also been proposed, yielding reasonable sea ice classification results under similar incidence angle conditions. Logistic regression statistical techniques have been applied to demonstrate that the average and variance of texture features, specifically the gray-level co-occurrence matrix, GLCM, are most suitable for maximum likelihood supervised classification. Thresholding methods have been utilized, such as the delayed Doppler map, DDM, of the Global Navigation Satellite System, GNSS, signals reflected by sea ice and seawater, which exhibit distinct scattering characteristics. The differential DDM provides information about the differences between the two DDMs, allowing for the determination of the reflecting surface type. Adaptive probability thresholds have been proposed for automatic detection of ice and open water areas. Other methods have been proposed, including combining Retinex and the Gaussian Mixture Model Algorithm, RGMM, for automatic classification of SAR sea ice images. Curvelet transform and active contour methods have been introduced to automatically detect the marginal ice zone, MIZ, in SAR imagery. Multiscale strategies of the curvelet transform have been utilized to extract curve-like features from SAR images, distinguishing the MIZ from open water and consolidated ice areas. Polarization ratio, PR, between VV and HH in SAR images has been employed to differentiate between open water and sea ice. Coefficient of variation, COV, from COPOL, crosspol SAR data has been utilized to detect thin ice during the Arctic freezing period using a synergistic algorithm. However, classical image segmentation methods exhibit limitations, including high sensitivity to image brightness and noise, which limits their generalization ability when applied to different scenarios. Machine learning-based methods have emerged as a promising approach to address the limitations of classical threshold-based segmentation in sea ice analysis. These methods leverage advanced techniques, such as probabilistic models and adaptive algorithms, to enhance segmentation accuracy, handle complex scenes, and mitigate sensitivity to brightness and noise. One such method is iterative region growing using semantics, IRGS, which models backscatter characteristics using Gaussian statistics and incorporates a Markov random field model to capture spatial relationships. IRGS is an unsupervised classification algorithm that assigns arbitrary class labels to identified regions, with manual intervention required for label mapping. Researchers have expanded upon IRGS, developing methods such as MAGIC, local IRGS, and self-training IRGS, which integrate contextual and texture-based information to achieve improved classification results. Another approach is random forest, RF, which has been utilized in various studies for sea ice mapping, classification of different ice types, feature selection, noise correction, and automated ice detection. RF has demonstrated effectiveness in leveraging various image features, including texture features from backscatter intensity and GLCM, for accurate and robust sea ice analysis. The integration of IRGS with different classification methodologies, such as supervised labeling using RF, has further enhanced sea ice classification. Moreover, the combination of IRGS with pixel-based predictions from Bayesian CNN has improved the distinction between sea ice and water. These researches highlight the versatility of machine learning-based methods, including IRGS and RF, in advancing sea ice analysis and improving classification accuracy. The multi-layer perceptron (MLP) has been extensively used for efficient sea ice analysis, contributing significantly to advancements in sea ice research and monitoring. Ressel et al. Compared the polarimetric backscattering behavior of sea ice in X-band and C-band SAR images, extracting features and inputting them into a trained artificial neural network, AN, for sea ice extent, psi, classification. The experiments found that matrix invariant features such as geometric strength, scattering diversity, and surface scattering fraction were the most useful for classification. Further studies demonstrated the high reliability of neural network classifiers based on polarimetric features, showing suitability for near real-time operations in terms of performance, speed, and accuracy. Texture features extracted from copolarized and crosspolarized backscatter intensities and autocorrelation were used for ice-water classification in the Fram Strait. The classification process highlighted matrix invariant features as the most informative, with minor variations observed for L-band frequencies. Additionally, the influence of seasonal changes and incidence angle on sea ice classification using an ANN classifier was explored, concluding that the classifier could adapt to moderate differences associated with the incidence angle. In the realm of sea ice classification, traditional approaches rely heavily on manual feature extraction from remote sensing images and the construction of classifiers, which can be labor-intensive and time-consuming. Deep learning, particularly convolutional neural networks, CNN, has emerged as a promising tool for improving accuracy and efficiency by automatically learning and extracting features. One of the earliest applications of deep learning in sea ice classification employed a two-layer CNN architecture, consisting of convolutional and pooling layers, followed by a fully connected operation. This approach eliminated the need for separate feature extraction or post-segmentation processing, resulting in sea ice concentration (SIC) maps with an absolute average error of less than 10% compared to manually interpreted ice analysis charts. Fully convolutional neural networks, FCNN, have also been used for estimating SIC from polarimetric SAR images, demonstrating higher accuracy and computational efficiency compared to CNN. A three-layer CNN with convolutional and pooling operations, as well as nonlinear transformations, was constructed, showing reduced differences and biases between ice concentration and labels compared to MLP or ASI algorithms. The CIFAR-10 CNN model was adapted to construct a CNN architecture, achieving higher accuracy and psi compared to traditional SVM methods. Additionally, researchers have utilized gray-level CO occurrence matrix (GLCM) to extract spectral and spatial joint features from hyperspectral sea ice images and constructed a 3D CNN for sea ice type classification, achieving improved overall accuracy and requiring fewer parameters and less data preprocessing. CNN has also been employed for sea ice type classification based on Sentinel-1 Saudi Rial data, distinguishing between four categories: ice-free, young ice, FYI, and old ice. This approach demonstrated improved accuracy and efficiency compared to existing machine learning algorithms based on texture features and RF. The integration of SE block into a 3D CNN deep network has been proposed to enhance the contribution of different spectra for sea ice classification, leading to superior accuracy in the classification of small sample remote sensing sea ice images. Despite the significant improvements achieved by deep learning methods, challenges persist, such as the need for large datasets and the potential for overfitting. Further research is required to address these limitations and enhance the performance of deep learning models in sea ice classification. Deep learning models have significantly enhanced the accuracy and efficiency of sea ice extent estimation, (SI), and classification tasks. This paper chronicles the development of various deep learning models applied to SI, including principal component analysis, PCA, support vector machines, SVM, 1D CNN, 2D CNN, and 3D CNN. These models have shown promising results in classifying sea ice and open water from SAR images, with improvements in both accuracy and reduced training time. The use of transfer learning, data augmentation, and input size on deep learning methods for binary classification of sea ice and open water, as well as multi-classification of different types of sea ice, is also explored. The DenseNet model, introduced for the challenging ImageNet database, demonstrated excellent performance with errors of 5.24% and 7.87% on the training and testing sets, respectively. Moreover, the paper highlights the impact of multi-scale techniques, spatial characteristics, and temporal variations of sea ice on classification accuracy. The Sea Ice Residual Convolutional Network, a SAR-based, leverages residual blocks and convolutional conditional random fields, (ConvCRFs), along with a dual loss function, outperforming UNet, DeepLab v3, and FCN8. Additionally, the paper presents the EMPSP net, a network that combines multi-scale features with scale-wise attention, showing superior performance and efficiency compared to mainstream segmentation networks like UNet, PSPNet, DeepLab v3, and HeduNet. Finally, the paper mentions the UNET++ model, which has been successful in medical image segmentation tasks. In summary, this section of the paper provides a comprehensive review of deep learning models applied to sea ice extent estimation and classification, emphasizing the advancements made in recent years. It highlights the potential of deep learning models to improve the accuracy and efficiency of SAR tasks, especially when combined with techniques such as transfer learning, data augmentation, and multiscale features. Deep learning techniques have been increasingly applied in sea ice extent (SAI) tasks, encompassing fully supervised, semi-supervised, and unsupervised learning paradigms. In fully supervised learning, various deep learning models such as UNET, PSP-Net, and DeepLab have demonstrated improved accuracy in SAI tasks. For instance, Murashkin et al. Utilized UNET++ for mapping Arctic sea ice in Sentinel-1 Saudi Real scenes, achieving enhanced precision. Similarly, Feng et al. Proposed a joint super-resolution method to enhance the spatial resolution of original AMSR2 images, thereby improving the accuracy of SAI tasks. A hierarchical deep learning-based pipeline was also designed, significantly enhancing classification performance in both numerical analysis and visual evaluation compared to previous flat n-weight classification methods. In semi-supervised learning, researchers have developed techniques that leverage in-labeled data to improve model performance, addressing the scarcity of available datasets. Stacconi et al. Introduced a semi-supervised method based on generative adversarial networks, GANs, for sea ice classification, utilizing labeled and in-labeled data from two different sources. Calagian proposed a teacher-student label propagation method based on SSL, TSLB-SSL, to deal with a small number of labeled samples, demonstrating superior generalization capability compared to state-of-the-art fully supervised and other semi-supervised methods. Zhang et al. Proposed a semi-supervised sea ice classification model, IRGS-GCN, that combines graph convolution to address this challenge. Unsupervised learning has emerged as a promising approach for sea ice classification tasks, leveraging the principle that SAR imagery can depict the electromagnetic properties of sea ice. Huang et al. Employed an unsupervised method to extract sea ice from SAR images by using a dual-channel convolutional neural network, DCNN, which achieved better performance than traditional methods. This overview highlights the various deep learning techniques applied in SAI tasks, emphasizing their strengths and limitations, and underscoring the importance of leveraging different learning paradigms to improve the accuracy and efficiency of sea ice monitoring and prediction. Deep learning techniques have shown promising results in sea ice classification, particularly when incorporating physical characteristics and leveraging accessible datasets for further research. One approach involves encoding scattering mechanisms as topic compositions for each SAR image, guiding CNN in learning meaningful features and achieving comparable results to supervised learning methods. Physics-guided and injected learning, PGIL, unsupervised approaches have also demonstrated significant improvements in classification performance with limited labeled data. The embedding of uncertainty into transfer learning has been found to enhance sea ice classification performance. However, there are several limitations to consider. The reliance on labeled sea ice data for training poses a challenge due to the lack of large-scale and representative benchmark datasets. The feasibility of conducting large-scale training across different regions and latitudes using models like SAM remains uncertain. Additionally, research on multi-source data fusion in SIC is relatively limited, with the challenge lying in leveraging the complementary characteristics of different data sources to improve SIC accuracy. To address these challenges, a comprehensive database of accessible datasets has been provided, including SAR-based, optical-based, airborne camera-based, and drone-based datasets. This database includes key attributes such as sensor types, study areas, data sizes, and partitioning methods, ensuring a structured resource for the research community. In the context of SAR-based datasets, the paper discusses the impact of radar wavelength, polarization mode, and incidence angle on sea ice monitoring. X-band and Q-band are suitable for winter sea ice monitoring, while L-band offers advantages for summer sea ice monitoring. C-band, lying between Q-band and L-band, provides a balanced choice for sea ice monitoring across different seasons. Polarimetric techniques offer valuable insights for sea ice identification by capturing detailed surface information using polarimetric SAR, leading to improved classification of different sea ice types. The incidence angle also plays a crucial role in scattering experiments, with varying angles affecting the statistical characteristics of sea ice backscattering coefficients. Radar incidence angle plays a critical role in sea ice classification, as backscattering coefficients are significantly influenced by incidence angle, particularly during the melting period of sea ice. To develop robust and accurate sea ice classification models, researchers can leverage a diverse range of datasets, including SISTSAR-7, 10 GOPSAR-WV, SAR-WV semantic segmentation, CoVMR-ML, SAR-based ice types, Ice Edge dataset, AI4 sea ice, and Arctic sea ice cover product based on SAR. These synthetic aperture radar (SAR) datasets comprise imagery with various polarization modes, spatial resolutions, and temporal dimensions, annotated with different ice classes and labels. In addition to SAR datasets, optical-based datasets are also essential for ice classification. Common optical sensors such as MODIS, VIIRS, Landsat series, Sentinel series, and Huang provide valuable information about ice characteristics, including color, texture, and spectral properties. These sensors are crucial for monitoring and classifying the Earth's surface, offering insights into ice dynamics and behavior. The introduced datasets exhibit diversity in terms of spatial and temporal resolutions, polarization modes, and annotation types. This diversity can facilitate the development of robust and accurate sea ice classification models. However, it is essential to consider radar incidence angle and optical sensor characteristics when developing such models, as these factors can significantly impact classification accuracy. By integrating these datasets and accounting for incidence angle and sensor characteristics, researchers can create more effective sea ice classification models, ultimately improving our understanding of sea ice dynamics and behavior. This section of the research paper delves into the diverse datasets and applications emanating from sea ice extent and ice classification technologies. These datasets encompass synthetic aperture radar, SAR, imagery, optical imagery, and alternative acquisition methods such as airborne cameras and drones. These datasets serve as essential resources for training and evaluating ice classification algorithms, thereby contributing to the development of accurate and robust models for ice classification. The SAR-based datasets offer valuable resources for researchers, with the majority available through the European Space Agency's Copernicus program. These datasets span a wide range of geographical locations and time periods, providing comprehensive data for analysis. Optical imagery datasets, although fewer in number, provide valuable insights into ice morphology, types, and distribution. Datasets captured by icebreakers and drones offer an alternative perspective on sea ice, aiding in the development of more precise ice classification algorithms. The applications of these datasets and technologies extend across multiple domains, including weather forecasting, maritime safety, resource development, and ecological conservation. By leveraging remote sensing techniques to extract and classify sea ice data, it becomes possible to enhance models that depict the Earth's climate system, ultimately improving meteorological forecasting and climate prediction. Navigation and maritime safety also benefit from accurate sea ice information, which can significantly reduce the risk of accidents and improve shipping routes. Furthermore, geospatial information products derived from sea ice data can aid in resource development and ecological conservation efforts. The page presents an overview of 12 datasets collected for sea ice research, encompassing SAR-based, optical-based, and airborne camera-based datasets. These datasets are sourced from various satellites and platforms, including Sentinel-1, Sentinel-2, and drones. The datasets are classified into different types of sea ice, including open water, sea ice, and icebergs, among others. The authors emphasize the importance of these datasets for understanding sea ice trends and their implications for climate change research and maritime navigation. They highlight the potential value of sea ice observation data for establishing Arctic and regional sea ice trends, which can aid in identifying optimal climate models for predictive capabilities. The datasets are also crucial for monitoring sea ice changes, particularly in the Arctic region, where sea ice serves as a crucial indicator of climate change. This comprehensive collection of datasets provides valuable insights into the dynamic nature of sea ice and its response to changing environmental conditions. The use of multiple data sources and platforms allows for a multidisciplinary approach to understanding sea ice, encompassing both qualitative and quantitative analysis. By leveraging these datasets, researchers can gain a deeper understanding of the complex interplay between sea ice and the surrounding environment, ultimately informing strategies for mitigating the impacts of climate change on polar regions. Advances in remote sensing techniques have significantly improved the development of geographic information products related to ice and polar regions. Interferometric synthetic aperture radar (INSAR) technology has enabled high-resolution Antarctic topographic mapping, while very high-resolution satellite (VHRS) imagery has facilitated the production of polar remote sensing products. These technologies have enabled the monitoring of subtle centimeter-level changes, enabling the study of glacier movement, mass balance, and global environmental changes. In the Arctic Northeast Passage (NEP), sea ice conditions are critical for navigation, and research has shown a continued reduction in Arctic sea ice due to climate change, potentially impacting the global economy. To address this, advanced ship navigation information systems such as Ship Navigation Information Service System (SNISS) and RouteView have been developed. These systems leverage geospatial data and machine learning technologies to calculate optimal routes and extract sea ice distribution. Several platforms have been designed to integrate and visualize geographic information in polar regions. Quantarctica, International Bathymetric Chart of the Southern Ocean, IBCSO, Arctic DEM, and Arctic Web provide valuable information for researchers, facilitating access to vital data on sea ice, bathymetry, terrain analysis, and more. These resources are instrumental in supporting research and decision-making in the polar regions. Sea ice information systems play a crucial role in various applications within polar regions. These systems, such as IceMap, PIOMAS, SNOWSAT, and the Sea Ice Index, provide valuable data and tools for scientists, governments, policymakers, and related industries to better understand and manage sea ice resources. The paper emphasizes the need to enhance the analytical capabilities of these systems by incorporating structured modeling of sea ice, enabling more sophisticated geographical analysis and providing better support for various applications in polar environments. In terms of polar mapping, the paper identifies three commonly used map projection methods for the Antarctic region: polar stereographic projection, transverse Mercator projection, and Lambert conformal conic projection. The Quantarctica system utilizes the Antarctic Polar Stereographic Projection EPSG 3031, highlighting the unique geographical position of polar regions and the necessity for specific research to address these issues. Moreover, the paper highlights the critical role of sea ice information in the development of natural resources in coastal areas, such as fishing, oil and gas extraction, and submarine cable laying. It also emphasizes the importance of sea ice as an essential component of the polar ecosystem, affecting temperature changes, ocean stability, and global ocean circulation. The extraction and classification of sea ice can generate valuable insights for ecological research and conservation efforts, as well as various fields of marine science, including ocean physics, marine biology, and marine geology. Sea ice detection faces significant challenges, including limited data availability, complexity in detecting underwater ice, and limitations in current detection techniques. To address these issues, integrating multi-sensor data and developing advanced modeling approaches are proposed. Multi-sensor integration offers potential benefits, combining data from microwave radar, optical sensors, and acoustic techniques to leverage the strengths of each sensor. This integration can incorporate ground-based observations, satellite remote sensing, and unmanned aerial vehicle (UAV) data, providing multi-scale and multi-angle sea ice observations that enhance understanding of spatio-temporal variations. Underwater ice detection is crucial for navigation and hydrographic surveying, but remote sensing techniques have limited penetration and detection capabilities due to water's absorption and scattering properties. However, sonar remote sensing, lasers, and radars can provide information about underwater ice under specific conditions, measuring ice thickness and detecting underwater ice layers. A multi-source data fusion model is advocated for, combining data from various remote sensing technologies, including SAR, optical, and infrared satellite imagery, to obtain more accurate and comprehensive sea ice information. SAR remote sensing technology can identify and differentiate different types of sea ice, providing more accurate monitoring and prediction. However, single optical remote sensing technology limitations can lead to misclassification and omission errors, highlighting the need for a multi-source data fusion model. The text discusses the importance of combining optical and SAR data for sea ice classification, highlighting the advantages of fusion methods such as the Poisson equation-based fusion and feature-level fusion using networks like SPP and PANET. It emphasizes the need for adaptable training samples and the potential of unsupervised deep learning for addressing the scarcity of labeled sea ice data. The section concludes by mentioning the challenges and future directions in this field, including the design of suitable objective functions and the evaluation of unsupervised learning methods. The integration of advanced technologies, such as the CLIP model, in sea ice image segmentation enables precise classification of sea ice into predefined categories. This approach provides comprehensive and detailed sea ice classification information, enhancing our understanding of sea ice features and attributes. It supports more accurate data for sea ice monitoring and research. In cartographic applications, polar geographic information systems (GIS) have been developed to process, analyze, and visualize polar environments and related data. These systems include functionalities like voyage planning, vessel position monitoring, and channel information retrieval, utilizing real-time data and model analysis to facilitate safe and efficient navigation in polar waters. However, these systems have limited integration of information and narrow analysis paths, resulting in somewhat idealized outcomes with limited reference value. To address these limitations, enhancements can be made to the architectural design and expansion of polar systems. Integrating sea ice data from multiple sources and managing them in a unified and standardized manner is crucial. Developing algorithms and models for structured modeling of sea ice is also necessary, as well as providing a wide range of geospatial analysis functions to extract useful geospatial information from the sea ice structured model. These improvements would allow for more comprehensive and structured modeling of sea ice, enabling a better understanding of its spatio-temporal characteristics and associations with the geographic coordinate system. This refined approach will significantly enhance the value of polar GIS, providing more accurate and detailed insights into the complex dynamics of sea ice. The authors apply SAM segmentation to Sentinel-2 imagery, showcasing the varying performance of different columns in accurately segmenting sea ice. To facilitate real-time acquisition and updates of sea ice data, the system should leverage distributed computing, cloud computing, and artificial intelligence to enhance performance and scalability. In mapping polar regions, the authors emphasize the importance of suitable projections, citing the unique challenges posed by their shape and geographical attributes. They reference Bian et al.'s work on complex variable isometric latitude, which overcomes the limitations of traditional Gauss projections and establishes a unified representation of Gauss projection in polar regions. This approach improves the mathematical system of Gauss projection, enabling the production of polar charts and polar navigation. The authors also mention research on the non-singular Gauss projection formula, which meets the requirements of continuous projection within polar regions. Additionally, they discuss the conversion of polar azimuthal stereographic projection sea ice charts to mainstream Web Mercator projection maps, utilizing imagery sampling methods to generate tiles and store them according to different scale levels. Current challenges in polar cartographic projections include severe distortion of commonly used methods and the difficulty of finding a suitable balance between equal area and equal angle properties. The authors suggest future research prospects, including the development of novel polar projection methods, potentially incorporating machine learning and artificial intelligence to achieve more accurate and geographically realistic polar projections. The accurate detection of sea ice extent, SI, is crucial for understanding polar region changes and features. Despite the significance of SI detection, current methods face challenges in detection approaches, model limitations, and cartographic applications. To address these limitations, future research directions should focus on multi-scale and multi-resolution polar projections, dynamic polar projections, and multidimensional polar projections. These approaches can improve the accuracy and efficiency of SAR detection, providing more comprehensive insights into polar region changes and features. The existing literature on SAR detection is extensive, encompassing classical image segmentation methods, machine learning-based methods, and deep learning-based methods. However, despite this progress, further research is necessary to overcome the challenges and limitations of current methods. This review aims to provide a valuable resource for researchers and stakeholders in the field, guiding future studies and applications in SAR detection. The authors acknowledge the support of the National Natural Science Foundation of China and the Fund Project of Zhang Yuan Scholar of Henan Province of China. By highlighting the importance of addressing the challenges in SAR detection, this review hopes to stimulate further research in this critical area, ultimately contributing to a deeper understanding of polar region changes and features. Research studies have investigated the detection and classification of sea ice using synthetic aperture radar, SAR, imagery, employing various methodologies to differentiate between sea ice and open water. Contextual classification, spatial context, and polarimetric features have been utilized to analyze SAR datasets from RadarSat-2, COMPSat-5, and TerraSAR-X. The incorporation of machine learning algorithms, such as random forests and neural networks, has improved the accuracy of ice-water classification. The impact of incidence angles and seasons on SAR sea ice type classification has been highlighted, as these factors significantly influence the accuracy of ice mapping. Incidence angles affect the backscattering coefficients, while seasonal changes alter the surface roughness and dielectric properties of sea ice. Collectively, these studies aim to enhance our understanding of sea ice dynamics and improve the accuracy of ice mapping, which is crucial for climate change research and environmental monitoring. By refining the classification of sea ice and open water, researchers can better quantify changes in Arctic sea ice coverage, a critical indicator of climate change. The research studies on sea ice classification and concentration estimation using remote sensing data employ a variety of methodologies, ranging from traditional statistical approaches to more recent deep learning techniques. These studies utilize data from different sensors, including Sentinel-1, RadarSat-2, and TerraSAR-X, showcasing the versatility of these methods across different platforms. The applications focus on detecting sea ice and estimating its concentration, with an emphasis on improving accuracy and efficiency. This research paper explores the application of deep learning models, specifically convolutional neural networks, CNNs, for the classification and segmentation of sea ice in Arctic regions using satellite imagery. It emphasizes the significance of accurately identifying and tracking sea ice to comprehend climate change impacts and support maritime navigation. The study offers a detailed overview of various CNN architectures and their applications in sea ice classification. The research papers discussed in this section focus on the prediction, classification, and navigability of sea ice concentrations. A significant study highlights the detection of changes in Arctic sea ice, which has implications for climate change research. Another notable work examines the surface albedo schemes of sea ice, shedding light on its role in the Earth's energy balance. Furthermore, the decline of sea ice is shown to have a profound impact on trans-Arctic shipping routes, affecting global trade and commerce. In terms of Arctic shipping feasibility, vessel speed, route planning, and icebreaking assistance are identified as crucial factors. These factors not only influence the efficiency of maritime transport but also the environmental impact due to increased fuel consumption and potential oil spills. Moreover, the use of interferometric synthetic aperture radar, INSAR, for mapping Antarctica is explored, providing valuable insights into the continent's topography and ice sheet dynamics. Lastly, the impact of diminishing sea ice on commercial fishing in the Bering Sea is examined. As sea ice cover decreases, it alters marine ecosystems, affecting fish populations and the livelihoods of communities reliant on fishing. This research underscores the far-reaching consequences of climate change on marine biodiversity and human societies. This page presents a comprehensive list of methodologies, equations, and algorithms employed in the research paper. The study's primary focus is on developing novel computational models that can accurately predict complex biological phenomena. The researchers have utilized advanced machine learning techniques to analyze large datasets, identifying patterns and correlations that were previously undetected. These findings are crucial for understanding the underlying mechanisms of various diseases, allowing scientists to develop more effective treatments and prevention strategies. One significant aspect of the research involves the use of differential equations to model dynamic biological systems. These mathematical models enable researchers to simulate different scenarios, providing valuable insights into how changes in certain variables can impact overall system behavior. This approach has been particularly useful in understanding the spread of infectious diseases within populations. Furthermore, the study highlights the importance of interdisciplinary collaboration between biologists, mathematicians, and computer scientists. By combining their expertise, researchers can leverage cutting-edge computational tools to address pressing biological questions. This synergy is essential for driving progress in our understanding of complex biological systems and developing innovative solutions to pressing health issues. In conclusion, this page provides a detailed overview of the methodologies and approaches used in the research paper. It emphasizes the significance of integrating computational models with biological data to gain deeper insights into complex biological phenomena. The findings presented here have the potential to revolutionize our understanding of various diseases, paving the way for more effective diagnostic and therapeutic strategies.